Boa tarde. Good afternoon. Buenas tardes. Goedemiddag. Zor beher. Добрый день. Bem-vindo ao IMPA. Estamos muito felizes para vocês estarem todos aqui. Eu acredito que todos participantes que trocaram o horário para hora de verão estão aqui, outros vêm daqui uma hora. Tem muitos participantes que não falam inglês bem nem eu, e então a língua oficial do congresso será inglês. Então, com licença, eu vou passar para inglês desde agora. Okay, thank you. Good afternoon. Thank you, everybody, for coming. So let me introduce the organizing committee. This is Aparecido de Souza from Universidade, Federal University of Campina, Grande. Dan Marchesin and myself, Alexei Mailybaev, we are both from here, from IMPA. I think this is probably the first event in Brazil with so broad interest in a porous medium. Here in IMPA we had a series of events in the past which included porous media as a part of the meeting, but the focus was more on computational and mathematical side. So now we decided to make it really interdisciplinary. This is not an easy task. Well, what is porous media? This week my wife asked me, okay, so she's not a scientist, what you do this meeting about porous media, what's porous media? I said, okay, this is something which has pores. So he asked, is this porous media? I said, yes. And this porous media? Yes. Only on the fourth try she pointed out to something which was not porous media, at least from my point of view. So porous media is really something really broad. So, of course, the interest comes from, big part of interest comes from industry. Well, the petroleum engineering, one of the major, but of course, there are much more areas where the porous media come out. Well, in civil engineering, in other parts of engineering, in biology, in physics, etc. So there is big engineering interest in porous media. Of course, there are many unclear facts from perspective of fundamental science, so the physics, chemistry come in, and since everything is described by equation, it comes down to computational sciences and goes directly to a pure math. So we know there are several open problems in pure mathematics, like proving existence, uniqueness of solutions, so it's already become just pure math. So this is a idea of this meeting, to join the people from different areas who are interested in porous media, mathematicians, physicists, engineers, etc. So in that way we can communicate, collaborate, even to learn to speak the same language. This is not so easy every time. And I hope that this meeting will really bring this connection between people in different areas. As you already mentioned, this meeting is related to INTERPORE, so International Society of Porous Media, for Porous Media. And tomorrow we will have a short meeting about establishing the Brazilian chapter of INTERPORE. So this will be some Brazilian structure which will help coordinating the activity related to porous media science here in Brazil. So tomorrow will be this meeting. Everybody is invited. So you have this small page inside the program. And INTERPORE also gave the scientific support to this meeting. We have, just a part of the organization, we will have a cocktail. Cocktail will be in a coffee room on the second floor above the stairs. So please come tomorrow after 6:30 after the talks. Then we will have a group photo tomorrow during the coffee break, I think during the first coffee break. So also please come. Then the lunch. For lunch, we have a restaurant here in IMPA, which is fairly good. And also the bus will take people who like to go for lunch to Coffee Floor, which is a good restaurant here close to IMPA. The bus will be going there and back, so we can separate. It's also a very nice place. If anyone has some problems, questions, so please contact anyone from committee members, and also Anki and Sami that you met during the registration. They can provide the help. Of course, please take care that you download your files before your lecture with the chair of the session. So this is a computer which will work to project the presentations. Okay, so thank you very much. So done.
Well, thank you, Alexei. I should say that perhaps some of you know me from other times. This workshop here was to idea and realization of Alexei, pretty much. So we should all be thankful to him, and I'll have an opportunity to say it again. He brought fresh ideas and methods. I personally like mathematics of porous media, and but that's I'm saying nothing really, because it's mathematics universal, and the problems in porous media are particularly challenging, and you find connections between such problems and others all the time. I'd like now to, before giving the word to Professor Hans Bruining from the Technical University of Delft, before doing that, I had to do something which I forgot, so I'll skip that. And Hans, please come over. Do I need to have a microphone? Yes, but it's noisy. Okay.
So I am really honored to be the first session chairman here, which I entirely owe to the fact that I am the only person in this room, I guess, or one of the few persons who can pronounce the name of the first speaker in a correct way. So I am personally very happy that I think for what Alexei said, that he wanted to have a multidisciplinary workshop. I think the best thing you can do is to invite Rien van Genuchten. We all, I'm always curious how this happens, but Rien van Genuchten in the petroleum engineering world, but in the ground world, he doesn't need an introduction at all. And everybody in the world is using his constitutive relations, which from my petroleum engineering perspective are relative permeabilities and capillary pressures. I'm sure he gives different names to them. But I have seen, if I see his first talk, that he's giving a talk on scale dependency of non-equilibrium flow, which actually would interest me also very much, but is, as far as I'm concerned, a completely different topic. Nowadays, Professor van Genuchten is working together with Majid Hassanizadeh in Utrecht, who is also a good friend of mine. And I think he is occasionally traveling backwards and forwards between Rio and Utrecht. So I'm happy to give him the floor for his first talk.
Right. Or can I, Yeah, clip it in. I'll just put it in there. Okay, Hans and Alexei, first of all, thanks for the nice introduction. It's an absolute pleasure for me being here. I've been in Rio now for a few years. My Portuguese, unfortunately, is still pretty ruined, but luckily we can talk here English. I want to start with a couple of slides that I got from Majid Hassanizadeh about the Interpore. And there were 15 slides. I had just a few left here. But the idea is to really congratulate Alexei and the group here for starting this Interpore chapter in Brazil. I'm very much supportive of this idea. And I'm sure it comes out in the next couple of slides. Let me see if that goes. Do I need to point? Yeah, here. You know, the mission statement, I think Alexei already mentioned it more or less, but to establish, you know, an international platform for people to interact about modeling, coupled to deformation, flow, and transport in complex porous media. This is, to me, a slide, and I kept this from Majid, is pretty much what the motive is, certainly from my perspective. We have so many different societies. They're all structured in a vertical way. And Interpore, as far as I can see, is the first one that tried to go horizontally across the various disciplines. And you see here, actually, you know, the various, you know, scientific computing, petroleum engineering, as Hans said, civil environmental engineering. My own background is more or less of radar zone hydrology and solid physics. So there are quite a few organizations or disciplines involved. But the main idea really is this cutting across areas and sectors and disciplines. So very often we go to our own disciplinary organization, we go to our own meetings, we have our own journals often, our own funding agencies, and so, and even sometimes our own nomenclature and the way we describe things. So this is one way of interacting horizontally between the various groups. Let me see here. And so some specific aims, and I'm sure that it duplicates a little bit what Alexei was. Very important is the interaction with industry. There's not just only academic. Linking modelers, theoreticians, experimentalists, providing a forum to exchange and so on, funding. Very important also, and I think is very unique for the Interpore group, is the involvement of students. So you can see here, certainly in the States and Western Europe, a lot of involvement of master PhD students, postdocs, and so on. Let me see if that... and it's growing very rapidly. It really started only in 2008. You can see that a lot of individuals, especially institutional members, are growing. Here are some of the academic contributors. You see a lot of different universities and so on, and then also in the industrial members. In addition to these, there are quite a few sponsors of the annual meetings and so on. And I should mention to Hans is that many years ago, when I was just starting as a postdoc, actually Shell tried to hire me, but in Houston, Texas, and but I decided to forgo that. And these are the main individuals. Now the real key driver, as Hans said, is Majid Hassanizadeh. I'm very privileged to be able to work still with him. I'm basically retired from the States. I work a little bit at the Federal University here of Rio de Janeiro, and then also conjunctly with the Utrecht University. And the last thing I want to say is there is a meeting coming up next year. It's the so-and-so much, about the 5th or so annual meeting, and that will be in Padova in Italy. Very nice area. See if you can make it. And that's it in terms of this little introduction. And then we would like to go to my own talk. there. Ah. Let me see what that goes. No, that's November. Interpore, PPT van Genuchten. Yeah. That one. No. Next, that one. No. Here. Wait. Ah, okay. No. You do. Good. Okay, so super. This is the talk this afternoon. Again, I'm with both the Federal University here in Rio de Janeiro and have also a part-time association with the Earth Sciences Department in Utrecht. The focus of my work has always been kind of what I would call the near-surface environment. So you have here on the lower right side a little portrait, but I'm very much focused on the unsaturated, the vadozone, the interaction with the atmosphere as well as groundwater. And the things that always driven me is really the situation of this coupled vadozone groundwater atmospheric system. And there are a lot of stresses involved. I want to name a few here that pretty well reflect why I'm quite concerned about things. The land surface of the Earth is increasingly being altered. 2 billion hectares of our surface severely affected by degradation. Think about agriculture, especially agriculture by any measure is the biggest polluter of our system. Unfortunately, we need them. Point, non-point source pollution, think about mining, milling activities, certainly also very much here in Brazil. Urban pollution, this does not really need a lot of introduction in Rio de Janeiro. Renewable water resources. This is a bit scary to me, is that the amount of water we have per capita, which used to be about 20,000 cubic meter per capita per year, is dwindling very quickly, and they estimate that by 2020 it's only about 5,000. And even here in Brazil you can see already increasingly the stresses, certainly in Sao Paulo and Rio de Janeiro, with all the rain that we're having. Yeah. And then there will be increased competition for water. And so the way we manage the near surface is extremely important in terms of the sustainability, the efficiency of how we use water, and then also keeping our pollutants out of the groundwater. This system is very, very heterogeneous. It's not a man-made porous medium. It's not also beach sand. It can be extremely heterogeneous. This is why our standard equations for the problems of water flow and contaminant transport have a number of limitations. And so the limitations have to do with the heterogeneous makeup of the medium. Think about fractured rock. Think about in soils. We talked very often about microporosity. You can have wormholes or root channels, aggregated soils. These are well-defined geometries. Unfortunately, not everything is also responding to this well-defined geometry. And so you can have what we often call preferential flow or non-equilibrium flow. They're not necessarily the same terms, but I use them here interchangeable. But you can see here that the flow pattern, this is a dye tracer experiment, can be extremely irregular. And this preferential or non-equilibrium flow, a lot of work has been involved. And we actually know a lot about these processes. And one aspect, of course, is the processes involved. Flow in rock fractures, macropores, funneling, sloping layers. Think about sloping layers, unstable flow, fingering, wettability problems. Non-equilibrium from a mechanical point of view, call it facilitated transport. These are processes, and if you look in the hydrology literature, in the soils literature, agriculture engineering literature, there's a lot of stuff known. We also work with models. And actually, when you go to the same literature, there's an enormous series of models available. And I'll be talking about a few of them. You know, the porous, dual porosity models, dual permeability. We have discrete fracture models. We have various pore scale modeling approaches. I'm a true believer of that. We have these random walk type approaches, fractional derivatives, and so on. And there's a lot of activity there, and it's needed. And then we have, let me see here. And then we have, of course, when we have the models involved, we also have the parameters involved, which is a big challenge, because the more complicated we make our models, the more difficult it is to define these things. So we know a lot about the processes involved. We have an awful lot of models. The problem is, as I can see, is that there is really no good way. We haven't really succeeded in converting all we know. Much of this is qualitative. How to put that in equations, how to put that in our models, without making them too difficult. Although that is relative also, because I think with the way, what is it, Brown's law, but the way the computers are becoming more and more powerful, we can make these models bigger and bigger and bigger. But how do we translate whatever we know into something that can be used? That's where I think the main challenges lie. So then I come to an outline. I probably have too many slides, so I'm going to just start slowly. I'm going to talk a little bit about equilibrium, the classical approach, equilibrium transport. I'll talk a little bit about non-equilibrium, first order. I spend a lot of time here, including the first order dual porosity models, the geometry-based formulations, and so on, how they relate. And especially I focus on the mass transfer coefficient. We'll see what I mean with that. I'll talk a little bit about variably saturated flow also. An example if we have time. And then a bit of a look ahead. Yeah. So the standard equations we use, actually we have a one-phase approach. We just assume that the air phase is continuous. We call it the Richards equation. It's a scientist that worked at the University lab where I worked for about 35 years also. And you can see here now a pretty standard equation. And then the transport equation also pretty standard. Of course, there are lots of other terms involved. We leave that out for here. And then with Dij being the dispersion tensor, pretty standard. Baer and others worked on that for many, many years ago. The important thing in this discussion will be the DL, the longitudinal dispersivity. You also have a transverse dispersivity. And one pretty important slide, certainly also in this talk, is the, let me see if I can go back. Yeah, is the longitudinal dispersivity. And this is a slide that Mary Anderson many years ago put together. Let me see here. 1985, something similar was done by Gelhar, by Bevan, by Jury, and others. But it shows that the longitudinal dispersivity is a function of scale of the transport problem. If we work with very small laboratory-type columns of a porous medium, that thing is generally in the order of 1 to maybe 10 centimeters at most. when we have very large systems, the dispersivity grows. Some people argue there should be a asymptotic end. Perhaps that's true, perhaps not. But roughly, the main line here is that the longitudinal dispersivity, that's the difference. The longitudinal dispersivity is about 1/10 of the scale, and then the transfer dispersivity is about 1/10 of the longitudinal dispersivity. These are pretty nice guidelines if we have to do a field scale transport problem. Of course, there's a lot of deviation. If we have a very heterogeneous system, think about fractured rock, think about microporous soils, it will be a little bit higher. And when we have a very nice B-sand, it may be a little bit lower. In that sense, I want to go back now a moment to some of the work we did many, many years ago with transport. And I'm going to go to the very small scale initially. So we work here at the scale of a laboratory column, let's say 10, 15, 20, 30 centimeters. And this is some work I did for my PhD thesis now too many years ago. But there we worked then with the most simple of simple equation, equilibrium 1D, where R is a retardation factor. Here you have that dispersivity, so you have a diffusion coefficient and then the longitudinal dispersivity. This is the pore water velocity, that's the Darcy-Buckingham flux divided by the water content. So we did some experiments. Typically, if you plot that as a spore volume, that's dimensionless time, you get these type of curves. This was at that time for tritiated water and hexavalent chromium. And you can, let me see if that goes. You can then analyze that. The standard equations, generally at that time, we put it in dimensionless form here. P is known as the Piclet number, and I mentioned T, dimensionless time, often used as pore volume. You can put some initial and boundary conditions. So you can solve that for both the resonance concentration and the flux concentration. This is what we use for effluent curves. And so here we get these data that are fitted. R is 1 and 1.3. Very nice fit. Now this is for a system where we have homogeneous sand. Very, very carefully packed, no macropores and so on. Another one, that goes, yeah. Another one that we were not so well, be able to fit so well is a pesticide that we worked on at the time. There was a lot of interest in pollution by pesticides, so conventional approach at that time was to do these small column experiments and see if we could describe it with the advection dispersion equation. And here we try to fit. Clearly, it doesn't fit very well. Typically for macroporous systems or aggregated or structured system is you have a relatively fast initial breakthrough and then you get this tailing that does not lend itself to the advection dispersion equation. So we started looking at other equations. So this was the medium that we used, a very relatively small aggregated material. Yeah. And so the idea there is then to divide the system, to start thinking about these aggregates. And whether it's aggregates or fractured rock, the ideas are the same, but you start thinking about micropores and macropores, and a lot of the fluid would go through the macropores. There would be then some exchange between the larger macropores and the micropores, supposedly by diffusion. It could be a little bit advective transport also. Another aspect that I come back later is that when we have adsorption, think about metals, think about radionuclides or pesticides, the surface area inside these aggregates may be much larger than the external surface area, so there will be a lot of adsorption here that also is very much dependent on that diffusional exchange. So we get these equations then. It really started out with Coates and Smith many years ago. We then tried to modify these equations by including adsorption. So this is where we call dual porosity transport modeling, called mobile immobile models. That's where one of these arrows will be no flow. So we would have most of the flow through the, or some of the flow goes through the fractures, and there would be no flow through the matrix. And then some of the equations that include now also adsorption. absorption effect. So we have here these retardation factors for the mobile and immobile regions. And then the water content is divided into two pieces, one mobile and one immobile. And then just a very simple first-order exchange term. And that can be put in dimensionless form also, similar as for the advection, the equilibrium model. So here we have basically the same dimensionless parameters, except that the two most important parameters are this dimensionless partitioning coefficient, you can say, that accounts for the division between mobile water and total water, but also where the adsorption sites are. So if we have no sorption, this will be just the relative fraction of water that's mobile. But then we also have some concern about where the adsorption may take place. And then a dimensionless mass transfer coefficient, pretty traditional description. So when we put that in dimensionless form, we get this. We can then apply it to our breakthrough curve, and of course we get a very nice description, much better than the earlier one. So this is kind of standard. A number of questions arise though. This does not go too smoothly. Okay, here is this exchange term here. When we talk about this first order mass transfer, what is this alpha, this mass transfer coefficient? And there are two aspects of it. First of all, it's a function of the geometry of the flow field at the local scale. And then the other thing is there is a lot of evidence, similar as the dispersivity, that the scale of the transport problem has a big effect on the value of alpha. So I spent quite a lot of time on this to show that, and that it is actually very important and generally has been pretty much neglected. First of all, the geometry. And the geometry is best tackled with what I would call geometry-based equations. They're essentially the same as these first-order models, except we go one step deeper. We start looking at a diffusion equation that governs the exchange or the transfer of contaminants from the fracture to the matrix, or from the macropore to the micropore region. So that's the diffusion equation. That CIM that I used earlier is exactly the same as before in the overall transport equation, except CIM is the overall averaged concentration of the matrix. So you can see it's an integral. So then in the transport equation, we can keep exactly the same, but now we use that with a coupled system of local diffusion, where the CIM is really the average. And with some continuity boundary conditions. And this can be solved. Let me see here. Well, we can put that in dimensionless form. This actually, I'm going to use that a little bit later, so it looks a little bit more complicated. And this is that dimensionless mass transfer coefficient. And then beta is the same as before. There. And we can solve this. There are a number of analytical solutions in the literature. The first ones that probably did that was a fellow called Rasmussen. Anders Rasmussen, who worked with Naritniks in Sweden. And they actually did this for spherical aggregates. It's very much a chemical engineering. That's the efficiency of packed beds. He did that for spherical particles. And I followed that pretty much. There's a little paper I wrote many years ago where we did the same for these rectangular voids. Siddiqui and a number of people there at the University of Waterloo did something similar, except the structure of what they got is a bit different. These equations are pretty nasty in the sense it's an integral of an oscillatory function and a exponential function that decays very rapidly. So you have to do that numerically, and it's not quite easily. But this person here, again, Anders Rasmussen, showed how best to do that with partial sums. Yeah. So this is an equation. So pretty nasty. These are you have to calculate the roots of the equations, and then a number of other terms with the hyperbolic sines and cosine functions. There's an approximate solution available for all these. I only show one here. Is when you neglect dispersion in the system. No dispersion in your flow domain, and then also you let the fracture spacing to go to infinity, which means that at very long times you get deviations. So this is the complete analytical solution, and then the solution with, I don't know what that is there, but with no dispersion and a very wide fracture spacing system. And so they compare very well. We also have here some data in this particular case of Grisak and Pickens, or Grisak et al., a very classical study that they did in 1980, again at the University of Waterloo. So then you get just a very simple analytic formula, which is quite useful actually. We can do that the same. I worked on cylindrical macropores. The idea is exactly the same, except the geometry is different. So now instead of these rectangular voids, you have now a big macropore, and then you have diffusion from the macropore into the matrix. The approach for that is exactly the same, and I'm going to just try to impress you with the, where is it? You can also put that in dimensionless form, with the analytic solution. Now you get really a big mess because you have these Burr and Bai functions and so on. And I did that many, many years ago, and I kind of left it on its own, and a couple of months ago I started looking back at it, and just for me looking at how I did that, I was getting nervous and tired, you know. I wouldn't be able to do that anymore, but we did that with Laplace transforms, and quite a challenge. These equations, let me see. Yeah, these equations are conceptually very, very nice. This is probably exactly what's going on. And my feeling is that the cylindrical macropore formulation is probably the most realistic. If you look at fractured rock and so on, it's not so that all the fractures are always completely, especially in the unsaturated zone, are completely filled with water. Generally, it strings much more, and you would have only partial interaction of the flowing water with the rocks. And so that would hint much more on a cylindrical macropore type geometry. Unfortunately, these equations are probably too complex to use in our numerical models. And if we could somehow go back to, this is the transport equation, if we could go back to this first order approach, this is the dimensionless formulation. This approach is extremely easy to implement in numerical models. Basically only two additional lines if you work with Fortran or so in your code. This will require a lot, this formulation, a lot more numerics. So the idea that we did then at the time was to compare actually, is there a way we can approximate this, make this an approximation of the more involved model? And the way to do that is actually to look at the Laplace transform. There are different ways of doing that. One would be to look at moments, first and higher order moments, and try to equate those. I work with the Laplace transforms. In fact, if you look at the radial diffusion equation here, you can solve in the Laplace domain CA. So you get here a number of things with these Bessel functions. And then you do the integral in the Laplace domain. You get this particular formulation. You can do the same here for this one in the Laplace transform. You know, this is just S times C in the Laplace transform. You come out with this is, because this term is very small compared to omega. So this becomes 1 minus this particular term. So you get this term for the first order model, and this term here you can approximate pretty closely by that term, and you can see that if we equate this part and that part, we can solve for the dimensionless omega here, the dimensionless mass transfer coefficient, in terms of geometric parameters that are in the sphere, in the cylindrical macropore model. This is the beta that I used earlier. Let me see here. So here's an example actually, where we use this particular This is in dimensionless forms. If we do this in the dimensioned parameters, we get this particular equation where the mass transfer coefficient is a function of the diffusion coefficient. We have the immobile water content. We have B here is the sphere of this matrix mantle around the micropore. And then B of A, I'm going to use that sigma 0 here, is that ratio of B over the micropore itself. And so if we use this in our equation to get this omega and then the alpha back, and then we predict the relative concentration versus pore volume. Here we have that for 3 values of the rate coefficient. So this is an example where we assume that the B of A is 100. So we have a very large matrix, a very small pore relative to the matrix. We assume beta is equal to 0.2, which means that 80% of the material is matrix and only 20% is mobile water. Then we get this. In this case, we don't assume any adsorption. But you can see that the first order model provides an extremely good approximation of the whole spherical, the whole cylindrical micropore formulation. And this is probably quite realistic again if we recognize that many preferential flow pathways in the unsaturated zone are more the fingering type as compared to a full system. And that full system I go now to. So this is for a ratio of 100. So we have a relatively small pore and a large matrix around it. If we make this smaller, now that ratio is only 5, you see that some deviations start popping up. It becomes even worse when we start actually looking at spherical aggregates. There the approximation, you can do something similar, is actually not working very well. So you can see that this approximation with the first order model works extremely well for systems that have, like the cylindrical micropores, a large matrix volume to surface area. We show that later in another paper. I'm not going to go into that for also the water flow. It does not work very well for systems that have a large surface area and relatively small volume, and that's the spherical aggregates. Spherical aggregates that the surface area is very large. So that's actually a system where the surface area is largest compared to the volume, while the cylindrical micropores, it's just the other way around. So this is one thing that is kind of hopeful, is that at least we can relate this transfer coefficient with the geometry of the flow field. And again, my own view is that these first order models actually work quite nicely. The other problem, though, is that this alpha is likely also a function of the scale of the transport problem. And here we start getting in trouble. And the reason is that if we start looking at these dimensionless transport formulations, and we're going to increase the length of the transport domain, then this mass transfer coefficient in dimensionless forms keeps growing and growing and growing. And what it really means is that in actuality, the system starts thinking that you get closer and closer to equilibrium. Let me do an example for that. So this is the villain in a way that makes it so difficult. Let me give you an example, just a very simple 1D transport problem. So we're going to talk about just very simple 10 centimeters per day velocity. D is dispersion. I just assume that the dispersivity is 2.5. No sorption. I assume that 60% of the system is within the matrix. And so, which means that the pore water velocity of the transport domain is this divided by this ratio. It becomes 25. Yeah? And I'm going to show you some distributions where this alpha, that mass transfer coefficient, is 0.01, 5, 20, so I increase it every time by a value of 5. And I'm going to show you the breakthrough curves at x is 20 centimeters, then 200 and 2,000 centimeters. First of all, 20 centimeters. This is the mobile concentration. It's a very small pulse. Think about the Dirac delta function, but very close. I forgot how long. This is the mobile concentration. Then you have the immobile concentration. Of course, that one lags behind the mobile concentration because of that diffusion process. So you see here for alpha is 0.01. It's very close. It comes out very quickly at x is 20 centimeters. And then the immobile concentration lags quite considerably behind. When we go to a large transfer coefficient, the red curves, they're pretty close. And then, so these are mobile and immobile concentrations, and then the total, these are resident concentrations. The total concentration is then simply the weighted average of those two in terms of this beta, or theta m over theta. So you can see here it's typical for these alphas. For very small, you have this initial, it goes down, and then it goes to the equilibrium distribution. So this is kind of the average. So you can see when the alpha is very large, it goes actually very close to the equilibrium distribution. This is for 20 centimeters. Now we have similar curves for 200. So now we increase the length by 10. And now really look closely at what happens with the concentration. It goes down very quickly. And the equilibrium part increases. This is for the mobile concentration, the immobile concentration, and the total concentration, the total resonant concentration. You have still a little bit of an effect, significant effect, when this alpha is very small. But when alpha gets fairly large, it really goes up. And the idea is exactly the same. Increasing the alpha or the length will have exactly the same effect. And now we increase it again by 10, so this becomes 20 meters, and you can see you get a complete equilibrium distribution. Except that for the different alphas, you get more dispersion. So this is C mobile, C immobile, and this is the average. They're all three the same. If we have a very high alpha, we get basically the equilibrium situation back, no preferential flow. If we have a small alpha, then you get a much more dispersed character. And this is pretty well known, and actually you can do like we did earlier with Laplace transforms or comparing second order moments. You can actually predict what the dispersion coefficient should be. So the non-equilibrium situation produces a distribution that is characterized by a much higher dispersion coefficient. What does this mean? Now it's really interesting, actually, because let me go back here. If this is true, what it suggests is that when we have a long transport domain, it goes all to equilibrium. Unfortunately, we know that's not true. Unless you have a very limited lateral exchange. And that I try to demonstrate here. If you do just a simple transport simulation and forget about all the parameters, but you have a source here and it goes down. This is a 2D transport problem. You have the longitudinal transport, and then you have the transfer dispersion. And so the transport domain is touching upon an increasing larger porous medium. And it starts including all kinds of heterogeneities that would be outside the longitudinal direction. And this is why the dispersion coefficient increases. If we have a dispersion coefficient just as a small little thing versus length, the dispersion coefficient would not increase. Sometimes you actually get front sharpening. There are a lot of studies that show that. So it's the extent of the transport domain, especially laterally, that causes the dispersion coefficient to increase, as well as actually the alpha to decrease in our formulation. So that's the dispersion coefficient then, and we have something similar go for the transport model. Let me go back here to the dimensionless equations. And so the villain here is this dimensionless mass transfer coefficient. If we go to a larger scale, it says the omega increases, we go to equilibrium. We know that's not true. And if we know it's not true, in fact, if we think roughly that the degree of non-equilibrium stays about the same, it really means that the alpha must decrease versus the scale. If we keep the same dimensionless parameters and we keep the same value of omega to get this non-asymmetric or symmetric breakthrough curves, then the alpha, where's my thing, must change as a function of scale, of the length of your transport domain. And that must be roughly, not necessarily, very approximate, a function of the inverse of the transport domain. This is actually in agreement with a number of observations. This is a study I like very much that a guy called Maraca did. I think he is in the Middle East somewhere. What is it? Not Saudi Arabia, the other one. But anyway, but he did a study I very much like. What he did was he went to a number of studies in the literature and started look at the value of alpha that was fitted to various distributions versus the resonance time. This is the resonance time. Beta is, remember the division of mobile water to immobile water, and also the fraction of absorption sites in there, the retardation factor. So the resonance time increases when R increases the length, and inversely proportional to the flux. And then here the log of alpha. He separated that in 3 different groups: non-aggregated soils, aggregated media, stony media. If you neglect that and just do a very rough overall figure through this, you get a line like this, and actually the alpha becomes indeed inversely proportional to the length, to the scale of the transport domain. It's very consistent with that idea that the alpha must decrease inversely with the scale of a problem. I have a few remarks. How much time do we have? Because I can talk and talk and talk, no problem. But I don't want to.
You have still
7 minutes. 17. Okay, fine. So I'm going to. Okay. So that's one. Now we're here in our. So I want to talk very briefly about the. This is basically a dual porosity approach. I want to briefly talk about dual permeability, also the mass transfer coefficient for water flow. Basically, I skipped that, and I hope we have time to briefly visit an example. But we can extend all this to dual permeability media. And the equations here are relatively standard. This is something that we worked out with Horst Gerke many years ago at the salinity lab. He is east of Berlin, Müncheberg. But the idea would be exactly the same as before, but now we do this for water. So the idea is now we have fast flow of water in part, but now also slow water. So we have now movement of water in both the fracture and the matrix, and then some exchange. And the same for solute. For solute, the exchange, and that is these cap gammas here, the solute exchange is now just not only by diffusion, but also by advective transport, because we have water being exchanged between the 2 domains. Yeah. I'm going to not further talk about this, but I want to focus a moment on the flow equations. I have to do this. And then, first of all, this gamma W. Now, if we do that the same here, these are uptake, these are sink, sources and sinks of water. Don't worry about that. But this gamma would be the same as that transfer coefficient, transfer approach, but now for water. There are many ways of modeling that. We can, of course, do a 2- or 3-dimensional thing, but if we also want to stay with a simple first-order exchange term, this is probably the most realistic, where we say that the movement of water is proportional to the average pressure head differences in the fracture and the matrix regions. And then alpha is a mass transfer coefficient for water. Some other approaches are in the literature where this is done versus water content. That doesn't make a whole lot of sense because water content is not a driving atmosphere. Relative saturation is already a little bit better, but this is probably the best, although numerically a little bit of a challenge. And then the mass transfer coefficient you can relate to geometry type parameters, similarly as for the mass transfer coefficient for solute. And one way here, so this is actually a geometry factor. This is not the same as beta as before. This is a mean size of your aggregate, so it would be half the fracture spacing or the radius of a sphere or something. Ka would be the hydraulic conductivity of the fracture matrix interface. And that's actually not too easy because we know that sometimes the fracture matrix interface has a different conductivity than the matrix itself. Think about coatings. Think about clay particles that adhere to marker pores and so on. And then the way we did this to evaluate that came out the best in terms of comparing the approximate model again with a very geometry-based approach numerically to just half of the hydraulic conductivity of the fracture and the matrix, or the fracture conductivity and then the pressure head of the fractures and the matrix. There are different formulations of that in the literature. Zimmerman in London, who used to work at Berkeley lab, and Conan and a number of others have put some perturbations of this in the literature, but we're quite happy with this. So, if this works, there we go. Problem, of course, with this formulation, it's very similar as these geometry-based equations. So this is still relatively simple, but it poses quite a lot of headaches. We need at least 3 conductivities. We need a conductivity of the fractures. We need a conductivity of the fracture system. We need the conductivity of the matrix system, and probably even the conductivity of the fracture matrix interface. The geometry, this and that. So rather than doing this, one approximation would be to go back to a dual porosity approach, where we start getting rid of this particular exchange term. And the way to do that is to multiply this by W, which is the fraction of the domain that is mobile, or the fracture domain, and then 1 minus W would be the matrix domain. So we multiply that by W, 1 minus W, and then we can eliminate this coupling term. And so we come up with a new Richards equation where now we have for the water content pressure head relation, we call it the water retention curve or the capillary pressure saturation relation, we have a dual function. And the same for the hydraulic conductivity. And what that comes to then is that you get, for the pressure head here, as a function of water content, there's a little bit of an effect on of the macropores. This is actually relatively small. If you look at experiments, is if you have a large macropore, the volume of the macropore can be very small. But it has an effect, and a huge effect, on the hydraulic conductivity. If you plot this here versus the on a log scale, again also versus the pressure head. And this doesn't look very much, but it's 1, sometimes 2 orders of magnitude. So this is the main villain in terms of producing this non-equilibrium transport. Quite a few papers in the literature that address these things in various forms, just basically the description of these type of curves. The one that I like very much and that we included in our models mostly is by a fellow called Dörner, Wolfgang Dörner in Germany also. But basically, it's not a complete, if you go back here, a complete, just a weighted average, but he also played a little bit with the tortuosity term in our equations. So you know you have not just necessarily one, but multiple porosity functions. And so this is what we work with a lot. The idea here is, this is just one example. We worked with a fellow, his friend here also from Texas, Binayak Mohanty. We worked with this in Riverside for quite a few years. But you can see here the idea. These are actually some field measurements where we used the small cores brought into the laboratory, as well as tension and filtrometer data and so on. You can see here clearly a dual porosity type of appearance of the hydraulic function. And then very much where we're concerned with always was if you extrapolate this to zero or that, there's a big difference. And this is well known in the soil survey circles, where that difference generally is about 1 to 2 orders of magnitude. So let me go on. This is not just actually a thing related to macropores. Actually, when you go to tropical soils, very often we see another bending of the curve, not just near saturation. So these are capillary pressure saturation relationships. These are two soils, and they're very much apparent often with tropical soils here, with lato soils and oxy soils, where you see actually the macroporosity problems near saturation, but then you see a second bending of the curve that's often very close to what we call the permanent wilting point, which is about 15,000 centimeters or 15 bar. Here's two examples, Rio Claro here and Linz. You can see here it goes down, and then you have another. So you get a kind of a triple porosity description if you also account for the macropore effects. Another soil that is very much known to have these type of effects are volcanic ash soils, or Andes soils, or endo soils. And these are some data that my friend from Japan, Nobu Torida, but they measured that with actually with a evaporation method. I'm not going to go into that, but you can see here for the retention function, you have here the first one and then the second one, which is also very low negative pressures, and the same for the hydraulic conductivity. And I'll skip the details, but these are soils that very often show actually triple porosity problems. This is actually a soil I want to mention here that has a very high relative saturation, these volcanic ash soils. You see here 0.75. So what all this means is that my favorite approach is not to use the complete dual permeability formulation, but to stick with the standard Richards equation, but have a dual porosity type formulation for the hydraulic properties, the unsaturated hydraulic properties, but then still using a dual porosity approach for solute transport. And then I had, I think, one example. We have a few minutes. I'll run quickly through. This is something we did here with a mining site in Brazil. They had a leaching pad here and some holding ponds with very nasty material that was eventually used to produce the metals. I'm not telling you which company it was, to give a little bit of a, well. This was a surfer plot of the, where is it? Come on. Of the pollution problems here. There was a leak actually. I should go back. There was a, come on. There's a leak in one of these, in this one, presumably, and so they saw that the water level in the holding ponds went down quite significantly. This is a surfer plot, so what we did actually use a cross-section here, as shown that we used in our numerical models. This is that holding pond that apparently had a rupture in the geomembrane. And then it went down. It had a level of water of several meters. So numerically, there was not necessarily an easy thing, but we calculated that the effective area of infiltration was about 8 meters. You know. And so what we did was a numerical grid here. You can see we had 4 different horizons. This was a granular or fractured rock, you can say, a granular aquifer, and then basically unsaturated zone. The water table was very roughly like this, and we tried to follow what was going on. We had an observation well not too far away from the source. So this is these are some hydraulic parameters. Let me skip that, and then some other things. We tried to simulate that. One important thing, let me go back here. One important thing was to get the recharge rate along the surface. Some of them had no flux, you know, because this was basically a geomembrane and then also some compacted soil. So we calculated the recharge rate just using basically vapor zone modeling with root water uptake. And the way then we estimated the recharge rate was actually, we had limited data, basically 8 years, so we repeated that. We did this vapor zone modeling, and we looked at the drainage rate at about 2 or 3 meters below the surface. And so what we did was we took a straight line through it, and we came to an estimate of about, 0.2 of a millimeter per day. Not overly important in terms of the overall hydrology, because we had basically, most of it was the flow from left to right, and then of course the source here. So these are some simulations we did for the SO4, the sulfate plume. Very, very bad material. Actually, there is a little, if needed, I don't know if we can, probably not, I could. Oh, let me forget about a little video. But it's really remarkable. This stuff went down, and then they noticed the level was decreasing, so they pumped it out. They repaired the geomembrane, but the damage was done. They did not really excavate too much. The damage was done. Stuff went down. You can see here it goes mostly within the granular aquifer. A little bit goes into the at least the simulations suggest into the fracture aquifer, and then actually very interesting. A lot of material stayed close to the capillary fringe, so a little bit was moving into the unsaturated zone. And these are the observation points at that particular well. So it has a very, for sulfate, a relatively homogeneous distribution in the granular aquifer. And in that well we had some nice, relatively nice observations of the metal here, so we used that, and then we did the plume movement of the metal. We had some isotherms which suggested that for the particular scenario, pH and so on was relatively uniform. So we did the simulation, and we got really, really bad results. This is with equilibrium transport, so that beta that I used earlier, remember? Fraction mobile, immobile, but also accounts for absorption. What they noticed that the maximum concentration at the well was about 3,500 milligrams per liter. And when we did the equilibrium simulation, and that came out at about 5 years already. Our equilibrium simulation suggests 175, way off. And again, KD. The KD was measured, pretty much a linear isotherm. And then the concentration is the 3 points right there by the observation well. We tried to finagle, we tried to play a little bit with the KD, but it didn't really help. If we made the KD smaller, the concentration went way up and so on.
Sorry to interrupt, but I think that I have no idea what everybody wants, because I think calculus is on the customs. Because that is a little bit more flexible in terms of time.
Yeah, I have half a minute, I'll finish. Okay, super. So what we did, we went to this particular model. We played with both that beta, remember, that mostly governs the location in time, and then this alpha. Remember this, that was that beta and that alpha. That's where we could play with a little bit. And we used this as a guide. And when we used that alpha, became very small, we could actually fit the well data pretty well of the metal here. Not perfect. Interestingly, if you even work with that first order model, you can actually generate 2 peaks. And we did that a little bit with certain values. And then the value here, very close to that linear relation that you mentioned with Maraca. That's it. Just what I call some things to think about. We still work with these kind of classical equations. They need many bandages. And it's good to have some alternatives. I mentioned, the continuous time random walk, the fractional derivative. Whether or not they're going to improve, I have my doubts also. But non-equilibrium flow transport probably the norm. A range of models exist. Are these acceptable? These dual porosity models would be nice. Dual porosity shape of the functions of tropical soils, especially also skill-dependent relationships. So if I had some time, I would spend a little bit more time on that. And then, again, the alternative modeling approaches. And I think especially the pore scale. So I'm very happy to see a lot of papers now where people look at pore scale phenomena where they can play with different aggregations, with different fracture matrix assemblages, or different scales, both longitudinally and laterally. And we're now working with some people both at UFRJ here in Rio, as well as in Utrecht, both experimentally and theoretically. And I think that's it, if I don't forget. Yeah. So thanks, muito obrigado. Special thanks to a number of people. And again, I would really congratulate again the organizers, Alexei and his group. I think this is a very, very important initial initiative that's being done here. Thanks. Any questions?
The organizers, whether I need to be strict or we like more to have a little bit discussion and maybe we are at home 5 minutes later. Is that okay? Yeah. So I think we have time for a few short questions. Who can I give?